All right, so in this lecture, we will talk about multiple reactions. So, solving reactor design problems for multiple reactions is very similar to solving reactor design problems when you have just a single reaction, except that we now have to take multiple reactions account into the rate laws. So, the different species are going to react across multiple reactions. Different products are going to be produced. Some of those are going to be across multiple reactions, others are not. And then also the solution procedure. So a key point in this lecture is that we cannot use conversion anymore to solve our problems. Of course, we can always write a conversion for a reactant, but we can't use that to solve a reactor design problem involving multiple reactions. And the reason for that is that the conversion only tells you how much of something is converted. It doesn't tell you how much of that thing went to produce one product in one reaction versus another product in another reaction. So when we solved reactor design problems where multiple reactions are involved, we have to do our solutions in terms of N or F. So we're picking the balances that are in either N terms or F terms, not X terms. So in reality, when we do reactor design, we are almost always thinking of multiple reactions. So if we put a bunch of compounds into a reactor system, very, very few times are we going to have the case where we only have one reaction. Most of the time, there are multiple reactions going on. So, and these multiple reactions go on. Some of those reactions are going to produce the desired product, so the product that we set out wanting to produce. Others are going to produce undesired products. Some are going to produce needed intermediates. So if you think about reactions happening in series, maybe one of the initial reactions produces an intermediate species that's needed to produce some product later on. However, some reactions are going to deplete needed reactants and intermediates, and so one of our jobs as chemical reaction engineers is to suppress those reactions. Some reactions produce harmful products. Some reactions have really high activation energies, so they're kind of latent under the reaction conditions, but they are highly exothermic and hence pose a problem with reaction runaway. That means we always need to be keeping those reactions in the back of our mind, even if they aren't occurring at any appreciable rate under desired conditions. But say the conditions just kind of slipped slightly outside of the desired conditions or the normal conditions for 10 or so minutes, and if that's a type of reaction that could turn on because of that, it's something that we need to think about. So we need to concern ourselves with all the reactions that could occur in a chemical reactor. So we have a bunch of chemicals together. What could happen? So we don't want to just think about the desired reactions because then we're not doing our job. We want to think about everything that could happen so that we can make sure that we control for it. This includes reactions that are thermodynamically or kinetically suppressed under operating conditions, but which could come into play under circumstances where the reactor moves outside of the normal operating range. And we'll get more into that when we talk about reaction runaway, but it's good to start thinking about now. In fact, most catastrophic reactor failures involve reactor designs that ignored such reactions. And it's not usually an intentional ignoring of those types of reactions, but it's a failure to recognize that they were possible. So with that, let's talk about multiple reactions. So there's several different kinds that we'll cover. So one type of multiple reactions is parallel reactions. So that's where I have a reactant, in this case we'll call it A, and A can form multiple products. So in this case, maybe A goes to form B and A goes to form C. Two different rates with two different rate constants, K1 and K2. So if I wanted to write the rate laws here, I would say assume elementary. And I can write rate laws for species A, B, and C. So the rate law for A minus RA. This is now going to have contributions from both reaction 1 going to B and reaction 2 going to C. So that's going to be equal to K1 times Ca plus K2 times Ca. So notice this is a rate of consumption, so A is being consumed in both reaction 1 and reaction 2. If I wanted to look at the rate of generation of B, that's going to be equal to K1Ca, and the rate of generation of C is going to be equal to K2 times Ca. So alternatively, I could write the rate of consumption of A is equal to the rate of generation of B plus the rate of generation of C. Another type of reaction is a series reaction. So that's where reactions take place in series or in sequence. So for example, that might look something like this. I have A going to form B, going to form C. And those have different rates with different rate constants. And again, if I assume elementary reactions or elementary kinetics, I can write the rate laws for the different species. So the rate of consumption of A is going to be equal to K1Ca. We'll say we could write the rate of consumption or generation of B here. Either would be intuitive. I'm going to write generation. So B is being generated by reaction 1. So I'm going to write K1Ca. But it's being consumed by reaction 2, so I'm going to say minus K2Cb. So that's the net rate of generation of species B. And in fact, I could go back up here. That's essentially what I've done here. Also, I've said this is the net rate of consumption of species A. Okay, so back to my series example. My last one is C. So I'll say the rate of generation of C is equal to K2Cb. This also means that I could write my net rate of B is equal to minus Ra minus Rc. Okay, so the next example is independent reactions. So, and what that might look like, I have A goes to B plus C with one rate law, one rate constant, and then D goes to E plus F. And I have another rate law, rate constant. So the rate laws for the different species here, we'd say minus Ra. And again, we're going to assume elementary. So Ra minus Ra is going to be equal to K1Ca. And then this is going to be equal to Rb and equal to Rc. And then we would say that minus Rd is equal to K2 Cd, which is also going to be equal to Re and Rf. So in this case, none of these species are involved in both reactions. So A, B, and C are involved in reaction 1. D, E, and F are involved in reaction 2. None of them are involved in the other reaction, only in the one. That's why they're called independent. The next category of reactions is complex reactions. These are going to be combinations of what we've seen. And this is the more normal scenario. So for example, we would see A plus B with some rate constant goes to C plus D. A plus C goes to E. And I'm just making these examples up. E goes to G, and I could write out my rate laws minus RA is going to be equal to K1 CA CB plus K2 CA CC, assuming elementary. Minus RB is going to be equal to, so if I make the assumption that all these reactions are elementary, and I write out the rate laws for the different species, A, B, C, D, E, and G. These are the rate laws that I get. I just did this off the top of my head, so you should check to make sure that I did this correctly, make sure that you agree with this. So basically, this is key point number one. When I have multiple reactions going on, I now have to write net rates for my species. I can write the net rates of generation, or I can write the net rates of consumption. It doesn't matter. For each species, I should do what's easiest for me to think about. The most important thing is to account for the different reactions where my species are coming into play. Okay, so how does this change our procedure for solving our reactor design problems? So one is what we just did. So constructing net rates. I'm going to underline that. So I need to include all of the relevant reactions and account for stoichiometry in the different reactions. So as we saw in the prior examples, now I have reactants reacting in multiple reactions. I have products being formed in multiple reactions. Some products are being formed in one reaction and then they're reacting away in another. I need to account for all of that in my rate law. So I'm going to write my rate law to incorporate the multiple reactions. The other piece is selecting the correct form of the mole balance. So before, when I have just one reaction, in many cases, I have the choice whether I want to solve the mole balance in terms of X or N or F. When I am solving reactor design problems involving multiple reactions, for the most part, I have to use N or F. So I can think of two exceptions to that rule. One, I have a single reversible reaction, so a reaction A goes back and forth to B. Two, and then when I say that, this is the only thing I have going on in my reactor is this reaction. The other scenario is I have a single series of reactions, and this is the only thing going on in my reactor. A goes to B goes to C. I can solve both of those examples in terms of X. Anything else involving multiple reactions, I have to use N or F. So I can always write a conversion for a reactant species, and that uses the same formula that was defined in Chapter 2. But when I have multiple reactions outside of these two examples, I cannot solve my problem any longer in terms of conversion. So conversion is an extent of reaction variable, but it only tells you how much of some reactant was reacted away. It doesn't tell you how much of that reactant went to one reaction versus another. So for example, if I scroll back up to this example, these complex reactions that we wrote down, and I wanted to write a conversion of species A, I could do that. The amount of A that comes in minus the amount of A that comes out divided by the amount of A that comes in. That's my conversion of A, and I can always do that. But that doesn't tell me how much A went to produce C and D via reaction 1 versus the amount of A that was converted into E in reaction 2. So it doesn't give me that information. So it cannot be used to solve the problem. In fact, if I try to solve a problem, this problem right here, in terms of the conversion of A, then I don't have enough equations to satisfy all of my unknowns. So I must solve this system of equations in terms of F or N, depending if I'm in a flow or batch reactor. And that's going to involve me writing mole balances for each of my different species. That will give me enough information to solve the problem. We'll say while conversion tells how much of a reactant has been converted in total, doesn't tell how much was converted via the different reactions. So for example, e.g., if I have species A, and we'll say that species A are these molecules here, and I have initially 4 molecules of species A, and I have one reaction, call this reaction 1, and I have another reaction 2, and reaction 1 consumes 1 molecule and reaction 2 consumes 2 molecules. Then XA is equal to 0.75, but that only tells me the total amount converted. It does not tell me the extent of reaction 1 and the extent of reaction 2, which I would need in order to solve the problem. Okay, so let's do an example to practice with this and also to practice with stoichiometry. So the following reactions are taking place in liquid phase in a CSTR. So what we want to do is write expressions for the net rates of A, B, C, D, and E and use them to calculate the steady state rates in a CSTR that is operating at these concentrations. So I'm going to do this writing all net rates of generation, just because that's a little bit easier for me to keep track of. So I'm going to do A as an example, and then I'm going to encourage y'all to pause the video and do B, C, D, and E. B, C, D, and E. And then come back and check against what I got. So for A, I'll say the net rate of generation of A is going to be, A is being reacted away in reactions 1 and reaction 2. So we need to account for A in both of those reactions. So for reaction 1, it's going to be R1A, and then reaction 2, it's going to be R2A. Now, R1A, we already know, is going to be negative, so we're given the rate of reaction 1 in terms of species A. So we would need to convert this rate of consumption of species A into a rate of generation, which to do that, we can just multiply this negative sign over here. Rate of generation of species A in reaction 1 is negative. For this part, the rate of generation of A from reaction 2, this rate law is given in terms of species D. So we have to use stoichiometry to convert this. So we're going to do that using the relative rates expression. So that is going to be, we'd say R2A divided by -1. So the stoichiometric coefficient on A in reaction 2 is 1, and A is a reactant, so that gets a -1. And we're going to say that's going to be equal to R2D divided by +3. So the stoichiometric coefficient on D is 3, and D is a product, so that's a +3. So that means that R2A is equal to -1/3 R2D. So then the net rate of A is equal to R1A minus 1/3 R2D. So at this point, you should pause your video and write the net rates for species B, C, D, and E. I'm going to do that while you're doing that, so push pause. And when you push play, you'll see all of the expressions written here. Okay, so this is what I get for the net rates of the different species with respect to the rates written up here and the rate constants. So you should check your work against these numbers. If you get a different answer than me, send me an email. There's always a possibility that I did some of the algebra incorrectly. But this is the skill, or this is one of the skills we want to practice in this lecture, which is constructing net rates using stoichiometry equations and taking into account the different reactions, or how the different species participate in the different reactions. The next thing to do would be to solve all of these expressions by inserting these values into the rate expressions. So at the given concentrations, if I substitute those concentrations into the rate expressions, this is what I get. And again, if you got something different than me, then please email me. It's certainly possible that I made an algebra error. So now let's do one more example. Let's take the same example and say we are operating this CSTR. The volumetric flow rate is 100 liters per minute. We already know the operating concentrations. The entering concentration of A is 3 molar. The entering concentrations of everything else are 0. So what's the volume of the CSTR? So to do that, we already know the rate laws, but we need to write the mole balances. So we're going to write a mole balance for each species, and we're going to write in F terms because we can't solve this problem in X terms. So the mole balance for a CSTR for the different species looks something like this. Flow rate coming in minus flow rate coming out, plus the net rate of generation of that species times the volume. So in this case, I already know what my different rate expressions are. The volume is what I want to solve for. That means I just need to know these terms. So for everything except for species A, this term is 0 because A is the only thing that enters. FA naught is going to be equal to CA naught, which I know, times the volumetric flow rate. This is a liquid phase reaction, so my volumetric flow rate is constant. That means all of these terms are going to be equal to the concentration, which are given, times the volumetric flow rate. So in the next video, I'm going to enter all of this into Python and solve it.